Hello, everybody. We will talk today about radiation chemistry. So this is the lecture to share. So now, if you remember, we discussed at the beginning the standard paradigm of radiation action that goes essentially from the physical zone, the physical process, down to the organ level, full organism level, the human levels, and even, as we will see, for radiation in the environment or even in space. At the moment, we have essentially here, so we finished the physics part. We saw the interaction of ionizing radiation with matter. Now, today, we will touch quite a big region in this scale. This is this region here, where the ionization occurs either in biological molecules, then you have what we call direct damage, or in water, which is of course more likely because about 70%, 75% of the biological material is water, so it's likely that you have ionization in water. You will have excitation and ionization. This we have seen is the physical interaction, but then you have dissociation, production of free radicals, diffusion. This is the so-called chemical stage. From next time on, after biology, we will go in the biochemical and then in the biological level. You know, from the now we will see the chemistry of water, mainly chemistry of water. We will see today. Then we will see the biochemistry, so the mostly the DNA molecule, because this is the most important target. Then we will see the cell, the tissue, the full human organism, the environment, and the space. So we are now, this time we are here, somewhere in between 10 to minus 15 and 10 to minus 6 seconds. I mean, from the initial deposition, that of course it's in the femtosecond region, you know, the first events are in the femtosecond region. We will cover today up to the microsecond region. For longer times, I mean, after microseconds, we already enter in the biological stage. So it's important to be precise. Radiation chemistry is the study of the chemical effect of ionizing radiation. Sometimes this is interesting. In the literature, you will find a lot of radiochemistry and a lot of nuclear chemistry. Now, this is a bit distinct from what we will talk today, because radiochemistry strictly is the production of radioisotopes. So it's how you produce radioactive isotopes that then you use, for example, in diagnostics or in therapy. This is a big topic in the medical physics course, so we will not discuss it in this course of radiation biophysics. Same for nuclear chemistry. Nuclear chemistry is actually the nuclear transformation. So how do you, let's say it's the old myth of transforming lead in gold. That was the goal of the alchemists in the Middle Age. As you know, this is not impossible. It's slightly expensive, but it's not impossible. It's called nuclear chemistry, and you can actually, by fission, you can produce or by capture of neutrons, you can produce new elements. GSI, actually in Darmstadt, is one of the main centers in the world for nuclear chemistry, because many elements have been actually discovered at the GSI, heavy elements. Also, we have to make a distinction with what we call photochemistry. Photochemistry is also a big topic if you work on the ultraviolet light, on the UV. The boundary is not so sharp, you know, because the energy, this 30 electron volt, let's say, is the energy of the most bound electrons, and this corresponds to a wavelength of about 40 nanometer in the vacuum ultraviolet. So if we go at shorter wavelengths, say you enter in the ionizing radiation region. So as I say, the direct effect of radiation is ionization and excitation, but a large part of radiation effects come from indirect effect, where indirect effect is the reaction of species formed from the solvent with the solute. So you make a chemical reaction in the solvent, which is typically water, and this chemical reaction generates molecules that then, and then these molecules then interact with the biological molecule and create a damage. This is called the indirect effect. Okay, so make no confusion between directly ionizing and indirectly ionizing that we have seen in radiation physics. You know, directly ionizing are charged particles, indirectly ionizing are neutrons and photons. In this case, we called about direct effect and indirect effect on whether the damage is directly on the biological molecule or is created in water, and then the chemistry of water is changed, and this new chemistry of water can then generate the damage. So this is shown a little bit here. This is actually for charged particles. You see, this is a carbon ion, for example, going through matter. And you see there is a Bragg peak here. There's a Bragg peak at the end. So it's the maximum energy. And there are different phases. You see propagation of ions, primary ionization in the medium, propagation of secondaries, electrons and radicals. These are the free radicals generated. Electron degradation of DNA, and then once you have a damage on the DNA, you start to have the biological effect. There are also other effects. We will discuss this. The local heating, actually the energy released can be so high that you can have local heating. And you see, let's say in the previous animation, you see, you see the electrons, the yellow electrons making the damage. You see the electrons here that produce directly that, but you can have free radicals, like here, this is a free radical, so it's a water molecule that is actually instead producing the damage in the DNA. So it's not necessarily the electron itself, but can be the water molecules. The scale of the times, you see, again, we go from some 10 to minus 22 seconds up to some 10 to minus 5, 10 to minus 6 seconds. As I said, we really go from the femtoseconds to the microseconds here. Now, the electron excitation, these are some examples of electronic and vibrational transitions. Of course, as you know, depending on the energy in a molecule, you don't have only electronic transitions, but you also have rotational transitions. And this is how this transition looks like in different molecules, let's say. But in photochemistry, but also in radiation chemistry, it's very important to study these things within the so-called G value. So the definition in a photochemical, the yield of a photochemical reaction is the ratio of the number of molecules divided by the number of quanta absorbed, really the H-ni, the photons. In radiation chemistry, the energy of the photon or the particles exceeds the binding energy of an electron, which is in the order of 10 electron volts, 13 electron volts. And a high energy quantum, like can be a gamma ray, for example, the order of the MeV, is not absorbed by the molecule. The energy is much bigger than the binding energy. So while in photochemistry, you are in the same order of magnitude between the energy of the photon and the energy of the binding of the molecule, here the energy is much higher. So we cannot really define it, the G value in radiation chemistry in the same way you define it in photochemistry, but still you can say that this is the ratio of the number of product molecules formed divided by the energy deposited in it. So you define in radiation chemistry the G value as how many molecules of a given type you produce per energy. And generally the units is not SI unit is molecules for 100 electron volt. That's the most common way to express the G value. This means in SI units, this is 1.036 per 10 to minus 7 moles per joule. Now, the energy-related value is very useful if chemical effects of sparsely and densely ionizing radiation have to be compared. Again, you know, they're not necessarily the same, but we have to start with the number of species created per unit energy. Now, this is the most important molecule that we will study in this course, and is the water molecule. It's, is not an easy molecule, as you see. This is the molecular orbitals of the H2O molecule, and you see that here you can see the different. Sorry, you can see the different energies. You see this is. Okay, this is the basic level is 600 electron volt, but you see the first orbital is at 37 electron volt, then you have 19, 15, 14 are very close, and this is the level. Here you go into excited states. So essentially, in radiation chemistry, this is the target, not the DNA. The target is the water. I say, what happens in the water? And essentially what happens in the water is shown here. Is this is a bit of a cartoon showing the different reactions, but you can see it quite clearly. You start with the water molecule. Radiation, like here, will produce quite a number of different elements. This point here means a free radical. So you have an electron which is now in an unstable position in the molecule. It's not in a normal orbital. It's attached to the molecule, but it's not in a stable orbital. And the free radicals are OH. Actually, this is probably the most important. The most important free radical for all kinds of biological effects. But you have aquatic electrons, that is really an electron which is loosely bound to the full water molecule. H free radical, O2 radical, and then products, stable products of the reaction of the free radicals can be hydrogen peroxide, H2O2, and H2, the hydrogen molecule. You see that the initial stage is like at the beginning, you always have ionization. And ionization means that you have an electron and you leave, let's say, an excited water molecule. After ionization, this is also, of course, is charged, is positively charged. For excitation, you go from a normal molecule to an excited molecule. And in this cartoon, you see all the different pathways that you can go. Now, as we have discussed before, the main point here is shown from the chemistry point of view, is shown in this cartoon. What happens? You see that you have a double bond here. Now, this double bond in this chain, which is a carbon chain, a pentagram, becomes now a single bond plus a free electron. This is called free radical. So that the free radicals are atoms, molecules, ions. In our case, is mostly molecules, but sometimes it's also atoms, that, like the H free radical. And they have unpaired electrons in an open shell configuration. So obviously they are extremely chemical reactive because they have a free electron and they are in an unpaired, in an open shell configuration. They have a very important role in huge number of fields, from combustion to atmospheric chemistry, to polymerization, plasma chemistry, biochemistry, and human physiology in general. They play a key role in aging. You know that so they are really one of the most important components of the chemistry in the biological organism. Superoxide and nitric oxide regulate many processes, such as controlling vascular tone. And radical and free radical are frequently used interchangeably. So sometimes you just say radical, but this really means free radical. Sometimes, though, a radical can be trapped in a solvent cage or be otherwise bound, because it's not so free sometimes. Now, one of the main role of the antioxidant is actually exactly the one of getting rid of the free radicals. You know, antioxidants are very popular. Even in the market, you buy a lot of things with antioxidant written. The main role of the antioxidant is this one. They donate an electron to the free radical, and then they stabilize the free radical. So, you know, this is superheroes and supervillains in the circulatory systems. You see, this is antioxidant kicks out free radicals. So the role of the antioxidant is the one of getting rid of the free radicals, you see. And there is a score actually used in radiation in chemistry, I would say generally in chemistry, is the ORAC score. And this stands for oxygen radical absorbance capability. So it measures the antioxidant levels of food or any other chemical substance. So if you have a high ORAC score, this means that what you are eating has a high capability of antioxidants. You will remove and stop a lot of free radicals. About the natural antioxidant, I mean, one of the funny stories that you probably know already is the so-called French paradox that was already seen in the 90s, many years ago, actually, in the University of Bordeaux. Not by chance, in the University of Bordeaux. This was an epidemiological study that was correlating the coronary heart disease with the consumption of saturated fats, and in particular cheese. You know, in France, of course, you have a very high consumption of cheese, but this very high consumption of cheese, which is normally correlated with the high level of coronary heart disease because of the cholesterol, essentially, the large increase in cholesterol. In general, in the French population, you don't see any particular higher level of coronary heart disease compared to countries that eat far less cheese than in France. And this was at least in part attributed to the antioxidant effects of polyphenols in red wine. Red wine is a very high ORAC because the polyphenols in the wine are antioxidant, and so they stop the free radicals. And interesting that in France they started to make a lobbying for wine as a healthy food, which is almost a contradiction in terms, because of course wine, as all alcoholic beverage, are not healthy per se because they always damage the liver. But of course, if their consumption is small, is limited, is not abused, then maybe the benefit that you get from the antioxidant are more than the risks that you have for the liver functionality. Now, the yield of secondary radicals formed from the reaction of the hydroxyl radical with the scavenger is given by the Schuler formula. The scavenger is like, as we say, is an antioxidant. Those scavengers are all those molecules that get rid of the free radicals. So the Schuler formula gives the yield of secondary radicals that you form when you have an interaction. In this case, you see here of hydroxyl radicals. This gives you, and this is essentially is a Michaelis-Mentis kinetics. If you know a little bit of physical chemistry, this is essentially Michaelis-Mentis kinetics. Now, the global scheme of the first stage is shown here. Let me go a little bit farther in the chain. Okay, here we are. So you have ionizing radiation. The target is the water. You can have excitation or you can have ionization. These are the two cases. However, in both cases, you can have, if you have excitations, if you have ionization, I'm sorry, the H2O plus interacting with another water molecule generates H3O plus and the OH radical. The normal electron emitted becomes eventually an aquatic electron. And you see that also from the excitation of the molecule, you can have free radicals. Again, this OH radical. You see that OH radical comes both from the ionization and from the excitation. And that's one of the reasons why you see the G value for the OH radical is relatively high, is 0.29 micromole per joule, while, for example, the G value for the aquatic electron is also relatively high. You see 0.28 micromole per joule, almost the same of this one, while the other products that are secondary products have value as lowest G values. Now, let's say still in the physical stage, so when you have ionization, you have these two entities, you know, the ionized water molecule and the excited water molecule. And here you have some more details. You see, for example, the reaction of the ionized molecule with the normal water is an acid-base reaction, and this is the product. And the excitation and cleavage of the excited molecule, the most probable cleavage is in two free radicals, but there are also other cleavage paths, like simply oxygen plus hydrogen. The electron, as I said, slows and then thermalized in two stages in the medium, if it's not making additional ionizations. Of course, we have seen this. I mean, if it is a high energy electron, the high energy electron can create secondary electrons or tertiary electrons, depending on the energy of the electron itself. So this is really the initial stage. Following the homogenization of the media, let's say after this initial trauma, this initial catastrophe, the media level is about 10 nanoseconds, so it's a rapid event. At this time, essentially, the medium is transformed in a medium of free radicals and molecules, which we have seen the G values here. By the way, I forgot to say that, but it's written here, that these G values are relative to gamma rays from cobalt-60, so the typical standard. So again, this is a sequence of the reaction we have seen already, the sequence of the reactions that you have in the radiation chemistry of water. And this is now the recombination process. So what happens to these free radicals? You see, for example, the hydrogen free radicals can easily recombine with another hydrogen free radicals, and you will have a hydrogen molecule. If you have a recombination of aquatic electrons, then you will have again H2 plus 2 OH minus. The recombination of two hydroxy radical, and this is interesting. You see, hydroxy radical that are among the most common output of radiation chemistry. Their recombination gives hydrogen peroxide. Hydrogen peroxide itself is toxic for the cell. So not only the free radical, but also the product of the recombination of the free radical is toxic for the cell. You know this very well because you use hydrogen peroxide for disinfection of the wounds. So and is so effective in disinfection because of course it kills everything there. Of course, other possible recombinations is the formation of water, the formation of OH minus, the recombination of the ionized H hydrogen and OH, of course, gives water again. And then you have again the possible production of hydroxy radical if the aquatic electron interacts with the hydrogen peroxide. What you see down here is always the range of the kinetic constants for all these kind of reactions. So during the first 10 to minus 12 seconds, the molecules don't move very much. Okay, so we are still, let's say, in where they are created, they stay where they are created. So at this point, the environment consists of what in chemistry are known as spores. So they are heterogeneous region. Generally, as we have seen, toward the end of the track of the secondary electrons, we have seen many times that the interaction of the electrons becomes much higher in the tail, let's say at the end of their track. And this spur in water, now these regions in water that we are creating, contains a lot of the surviving species, you know, like the free radical and the aquatic electrons. These are examples, you know, that how the different free radicals appear at the end of a track of secondary electrons. There is, of course, the radiolysis of water depends on many factors. One factor is, of course, is the temperature. The temperature has an effect on the rate constant and on the diffusion constant of the radicals. This is the so-called Arrhenius behavior. If you study chemistry, this is obvious. The activation energies are relatively low, is only 10, 12 kilojoule per mole. So in total, let's say the yields are little modified by the temperature. So if you cool the samples, or if you heat up the samples, the activation, the total yields are not severely modified. Of course, the situation will change with the LET, with the radiation quality. The probability of short track, of course, increase with LET depending on where are the spurs. And, which is very important, the recombination is much more probably when you go to high LET, because now you create the free radicals very dense, at a very high density. They are very close to each other, so it's much more likely that these free radicals will recombine. So, make no mistake, the yields of radicals decrease as the yield of molecular produced increase with the LET. So essentially, because you make more damage, but this damage is localized, at the end you will end up with less free radical because you have recombination. And this is the track structures, let's say, showing what in chemistry are called spurs, you know, these regions where you have a lot of events. This is the typical track structures with the electrons and secondary electrons generated. And now look at the G values for two different LET. 0.2 LET, which is typically typically gamma rays. Gamma rays, photons from gamma rays have an LET around 0.2 kb per micron. 61 kb per micron is typically, if you remember, is the dose average LET of the fission spectrum neutrons. So it's a relatively high LET, not as high as alpha particles, which is more than 100 kb per micron, but much higher, of course, than photons. So you see that, interestingly, essentially all G values are reduced when you use high LET, including, for example, the OH radical goes from the very high level of 0.27 to only 0.091, but the G value for the recombination products, like hydrogen peroxide, goes up, because now you are making more recombination than you were doing before. Okay, and this is let's say an explanation of what I just said. These are other, now, what exactly happens in the presence of oxygen? This is extremely important in radiation biology. Now, of course, you know that in our body we have oxygen. We have oxygen virtually everywhere because we need oxygen to keep the tissue healthy. And this oxygen is generally in the form of molecular oxygen, so it's O2. Now, when the free radical will interact with the oxygen, generates reactive oxygen species, the so-called ROS. You see that there are many types. For example, you can create a superoxide radical and hydroperoxyl radical. You can create an in this way, from the HO2 radical, you can create a superoxide radical. You can still here have, you see, other ways of combining the radicals that will end up with the superoxide radical, the O2 radical. Now, this free radical is, and you see also here, this is the generation of oxygen radical. How can you generate oxygen radical? These free radicals, these reactive oxygen species, let's say, are extremely, extremely important. They are extremely important essentially because they boost quite a lot the radiation effects. So in the presence of oxygen, you will have more damage from radiation all the time. This is essentially due to what we call radiation fixation in general. So what you have is that if you have the interaction of a reactive oxygen species with any kind of biological molecule, you will fix the damage here, plus you have another radical. There are essentially two effects of the oxygen radicals. One is on the diffusion. So if the radical is fixed with oxygen, it will diffuse much more in the medium than if it is not linked with the oxygen. The other one is the fixation of the damage. So if it is a reactive oxygen species that interacts with the molecule, you will fix the damage. Will not be the reaction will not give an unstable molecule that then can be repaired, will give a stable damage. This paves the way, if you want, to the hypoxia problem. Now, of course, we will come back to the problem of hypoxia, because as you can imagine, hypoxia is one of the main problems in cancer radiotherapy. Not only radiotherapy, actually, in general in cancer therapy, because you see, this is the distribution of the oxygen in our body. If you have a capillary here, this is where the oxygen is flowing. It's flowing in the blood. You know this. It's always flowing in the blood. Now, from the blood is diffusing in the tissues. But if the tissues are far away from the capillary, they are less oxygenated than those tissues that are close to the oxygen. Now, if you have a tumor, of course, the tumor will grow quickly and the capillary will not reach this new growing region. So this means that large areas of the tumors will be hypoxic. This hypoxia is translated in radioresistance. These are in vitro experiments. We will learn how to read these curves. But even clinically, you see, maybe I can show you. This is the progression-free survival, which is not really the survival of the patient, but is how many years, this is years here. How many years after the treatment, the tumor is not in progression. And this is actually uterus cancer. And you see, this one up here is our oxic tumors. And this one down here are hypoxic tumors. So you see that when you have hypoxic tumors, the prognosis is very green, is very bad. When you have oxic tumors, which means sensitive, they are more sensitive because of the generation of reactive oxygen species. This is much better. And there is a dependence on the LET. When you increase the LET, we will come back to this point, this effect is reduced. Because we have seen it already, the formation of free radicals become less important. It's the direct effect, not the indirect effect, which is important when you go to high LET. So this is in general the definition, the book definition of reactive oxygen species. They include oxygen ions and peroxide and can be inorganic and organic. They are, of course, highly reactive. We have seen this. Actually, ROS, this is important to point out, are a natural byproduct of our metabolism. Because we live, we produce ROS. And they are not useless. They are not only bad. They are very important in cell-to-cell signaling. So they are not there by chance. Of course, the environmental stress and also the internal stress somehow apparently increase the level of ROS, and this produce the so-called oxidative stress, and the oxidative stress is strongly linked to a large number of diseases, but it's essentially strongly linked to aging. So it's a key role in aging. The raw sources, this we will see in the biology lecture, that they mostly come from mitochondria. So it's a natural product. It's a natural product of the metabolism of the cells. So we'll see this later. And there is now a topic where oxygen is becoming very important. It's the so-called flash radiotherapy. This is only a joke, but because of flash, of the word flash. Flash really means very high dose rate. So you see, this is the dose rate, so the greater minute, how quickly you deliver the dose. And this is the dose rate effectiveness factor. So you see, if it is high, this means that the effect has to be divided by a factor. So it's lower. Make no mistake, it's the invert of the effectiveness. So you see, when you go to low dose rate, when you have environmental exposures, the dose rate effectiveness factor is about 2. So the effect that you have giving the same dose in a long time is smaller. This is because we can repair much better because it's in long time. So you see, in environmental exposures, the effect is much smaller than the effect that you have in radiotherapy, where you give IMRTs, intensity modulated radiotherapy. Brachytherapy, which is internal radiotherapy, can also be relatively low dose rate because you implant sources in the tumor. But and these are different techniques. What happens here in this region of extremely high dose rate, what is called flash, is still not very clear. Actually, there are several data showing that when you go to very high dose rate, something like 40 gray per second, the normal tissue is spared. You have no effect on normal tissue, which is strange, you know, because you will say normal tissue has high oxygen concentration, so the effect on normal tissue, unfortunately, because of the oxygen concentration, is strong, and is the limitation that you have in the treatment of cancer. Why at 40 gray per second this happens? Well, maybe one of the reasons is an example. You see, these are original data on the induction of fibrosis in mice. So it's a normal tissue complication, the fibrosis in the lung when you treat lung cancer. These are the weeks after irradiation, and this is the percentage of animals showing fibrosis at 1.8 gray per minute, which is the normal dose rate used in radiotherapy, or 60 gray per second, which is a very high dose rate. And you see that is enormously lower. So you really have no side effects when you go to this very high dose rate. So, and this is now going to the clinics. You see, this is a paper published in July. This is mostly driven by the French groups, but everybody's following it up. In July 2019, the first patient was treated with flash. Of course, this is done with electrons. It's not easy to have this very high dose rate when you want to have X-rays, because, you know, to have X-rays, you have to convert from the electron energy into Bremsstrahlung. And this conversion factor is so negative, let's say so small, that to reach this very high dose rate with the X-rays is extremely difficult. At the moment, there is no machine that can do it, even though they are working on it, but you can do it with electrons. So this patient was actually treated with electrons. Now, what is the idea? Say, why the normal tissue becomes more resistant if you irradiate in a flash? Well, the basic idea is that you are depleting the oxygen if you have this oxygen hypothesis. You see, this is a common idea now in the community. It's not very clear. We will see. Of course, during the physicochemical stage, the molecular oxygen is consumed. You see, these are typical reaction where you create molecular oxygen. Now, this depends, of course, on the dose rate, sure, on the total dose, and on the consumption. So the problem is that if the rate is much higher than the diffusion in a given volume, you know, if you give the dose in a time which is much shorter, you consume the oxygen in a time that is much shorter than the time of diffusion of the oxygen, then you have a depletion of the oxygen. So your tissue is now behaving as an hypoxic and hypoxic tumor. So you have lower ROS level, lower damage fixation, mimicking radioresistance of hypoxic areas. And the regions that are already hypoxic, like the tumors, will not be very much affected. So this makes sense, except that, I'm not going into many details here, except that if you use a code to calculate, you see, this is again is a refined Monte Carlo calculation of all the steps, the chemical steps in the literature, you end up, you can show, you know, this is the ratio, let's say, of flesh versus conventional dose rate irradiation. And you can show that generally, you see that in the typical, in the solid lines here, the ratio is very close to 1. So if you, let's say, if you use the oxygen, there's still something we don't understand. If you use the oxygen depletion hypothesis, it doesn't really fit. It doesn't really explain. You see it quite clearly here. This is the dose weighted with the oxygen enhancement ratio. So with the factor that gives you the enhancement for the hypoxia. But you see that as long as you are at 7%, 5%, but even 3% or lower, you see in this region, because these are huge doses. So if you are in therapeutic doses that are essentially down here, with the normal tissue, so high oxygenation ratio, there is no difference. You see a ratio actually when you have very hypoxic. Then in that case, you change the ratio because you have very little oxygen. But when you have a lot of oxygen, unless you go to tremendously high dose, you see no effect. So this is still a hot topic, it's still open. We will come back to this when we will do radiotherapy, but actually probably in the medical physics course. But this is to show you that to explain this effect, you have to go back to the radiation chemistry. You cannot do it with the radiation biology or with radiation physics. So the direct, indirect effect we have seen, and we have also seen then that if you use scavengers that can remove free radicals, can remove ROS, you will reduce the indirect effect. One typical scavenger is the DMSO, dimethyl sulfoxide, which was very popular in the old times because is an anti-freezing liquid. So you used to put it, for example, in the radiators of the cars to avoid that the water, the cooling water in the engine becomes frozen during the winter. Now they're completely different systems, so you don't need it anymore. But the dimethyl sulfoxide is a typically anti-freezing molecule and is an excellent radical scavenger. And in fact, you see, if you use these radical scavengers for UV, for example, for UV, this is the quantum efficiency as a function of the photon energy for single-stranded breaks and double-stranded breaks in UV. So we're talking about UV. This is the quantum efficiency is like the G values as a function of the energy. And if you look at the damage in the DNA as a function of the dose induced by UV, no scavenger, you see clearly a very large difference because now you are getting rid of the reactive oxygen species. Now, as I told you before, this is a little bit strange. If you use ionizing radiation, you would expect that for X-rays, you will have a very large effect of a very large indirect effect. As a matter of fact, you see it here, the contribution of indirect action as a function of LET. The contribution of indirect fraction, you can just calculate adding a scavenger. So you add the scavenger and you see how much the survival in this case of the cells is changing. So you see, if you go to low LET, like the LET typical for gamma rays or X-rays, you are in the order of 80%. So in photon, so you see, it's very important. When you talk about X-rays, about 80% of damage is done by free radicals, is done by reactive oxygen species. When you increase the LET, if you remember, I have less free radicals, and it's more likely, though, that I have a direct effect, because if I have a track of ionization, it's very likely that along this track, I will have direct ionization of the molecule. However, this is interesting. Even when you go to extremely high LET, you see more than 1000 kb per micron in water, you still have a contribution here of indirect, which is a bit contradictory with the idea that the G values for the production of radicals at this LET are essentially zero. There is no free radical production. Everything is recombined. So this could be due not to the free radicals themselves, but to the products of recombination of the free radicals, like, for example, hydrogen peroxide. We can anticipate here, let's say, the next step that will be going from radiation biology to radiation chemistry, to radiation biology. And this is the important thing to say. The main target for radiation-induced cell killing is DNA. This is mostly for two reasons. I mean, one is that DNA is big, is a very long molecule, about 2-meter molecule packed in 10 microns of nucleus. So it's a really dense molecule, very big molecule. So it's very likely that you damage. And moreover, unlike essentially all other biological molecules, proteins, lipids, sugars, everything you want, there is no redundancy. So essentially you can damage a protein, doesn't matter, there are other millions of that proteins. But if you damage the DNA, we will see there are only 2 copies of the DNA, or even 1 copy in G1, if you want, depending on the cell cycle phase. There are many other evidence, let's say, that the main target is the DNA, and we will see them when we will go to radiation biology. Keep in mind, however, that this is the so-called classical paradigm. In recent years, it has been shown that there are also non-targeted effects where you can have even lethal effects, not directly hitting the DNA, but, for example, hitting another cell. Now, when you have the DNA and you want to see the damage on the DNA, this is the DNA, the track structure, this we have already seen, is extremely important. I think this picture was already shown in the previous lecture, is the track structure simulated with the Monte Carlo code for protons in water and carbon ions in water, and you see a clear the density of the damage here when you go to high LET radiation. There are several track structure codes that can calculate also radiation chemistry. This includes, you know, ChemCurbook, ParTrack, Gen4DNA, and so on and so forth. These are very useful codes because at this point, you see, you can essentially calculate all the diffusion coefficients for all kind of different chemical reactions and make simulations that are very solid. This is now an example, I think is very interesting, an example of the track of an alpha particle. If you remember, we saw these pictures already in the physics, and this is actually the physics, if you want, because this is now the particle is coming out or going in, is the same, it's coming, let's say it's coming out of the screen. So you see the core here, and you see the delta rays here. Red is an excitation event, and black is an ionization event. We are still here in the physics stage, but you see, when you move to the chemical stage, now you can generate all kind of free radicals here, and you see that the track structures becomes, of course, is loose. You know, when you go to 10 to minus 7 seconds, when you are in the microsecond region, there is no more track. So all the radicals are diffused. Now we are out of the chemical stage. If you want, we enter into the biological stage, and the chemical stage is here, is when how you go from the initial physical deposition to the generation of free radicals and to the migration of the free radicals in the medium. This is shown also here quite nicely. This is a track. This is the time, you see. And this is actually a zoom is a different scale. But you see very nicely here, as far, if you let's start from the beginning. Let's say when you see the appearance of the track, now is essentially the physical track, and you see that with the time, the shape of the track becomes more and more loose. You see, become broadens up, and eventually, essentially disappear. You see here, you know that. I'm sorry, it's not a zoom in space. Is a zoom in time, if you want. It's a different time scale that really shows you how the track out of the chemical stage, when you go then in the biochemical stage, you are lost. And these are actually images, you know, the evolution of 10 keV section of a 5 MeV helium ion in water. So the simulation starts at the bottom and continues with the primary interactions until the incidence helium ion has lost 10 keV. And you can see it here. You see secondary electrons that are produced. All secondary electrons lose energy by collision. And when you are already in the picosecond region, you see the ionized water molecules have decomposed to give a number of reactive radical species. It's interesting. You see now you are from the femtoseconds to the picoseconds, and now you essentially have all the free radicals now done. And at this point, you see at 100 picoseconds they are still there, and then in the nanoseconds region you start to see the diffusion. You start to see diffusion, and eventually you see this is 10 nanoseconds. 100 nanoseconds now, and essentially now the diffusion is so strong that they are essentially gone. You see, this is the 1 microsecond, that conventionally 1 microsecond, that says the end of the chemical stage. Okay, these are just difference in the track if you change the energy, but this is mostly due to the physics. One last point I want to make is that there are also other effects, very interesting effects in radiation chemistry that are hot topics in research now, but their really relevance is not completely clear. So at the moment, the image is pretty clear. No, you have ionizing radiation, you have ionization and excitations, either directly in the molecule, in the biological molecule, say the DNA. 20% of the cases, if it is X-rays, 80% of the cases the other way around, if it is high-lit radiation. But in any case, this is the direct effect. For sparsely ionizing radiation, most of the effect comes from the radiation chemistry. So you deposit the energy in water, you create free radicals. In the presence of oxygen, these free radicals fix the damage on the DNA and have a longer diffusion, a longer diffusion space. So this is let's say the normal, let's say clear picture that, if you want, is represented here. You know, either you have a direct effect, the electron that is actually ionizing the DNA molecule directly, or you have an indirect effect. You see, you create a radical, actually you see 4 nanometers, the DNA molecule is 2 nanometers diameter. So 4 nanometers is just a little bit bigger, because, and then it goes here. In the presence of oxygen can be formed even far away, but this is essentially direct effect and indirect effect. There are, however, other effects under study, and these include the thermohydrodynamical effects, which is interesting in a way. This is the temperature here. In this plot, you see the temperature at 2 nanometers. The local temperature, so the temperature in the 2 nanometer region, can be extremely high. Can be extremely high because you have a high energy deposition in an extremely small volume. Now, if you remember, a little dose for an organism is comparable to drinking not even a full cup of coffee, just a sip of a cup of coffee. But this is for the full organism. If you go in the nanometer scale, then of course the Bragg peak or even the tail of the electron, I mean, can deposit relatively, the ratio, let's say, of the energy to the volume is so high that the local, if you define a local temperature, this local temperature will be extremely high. Now, what is the meaning of that? This is what is the meaning of temperature when you go in the nanometer. You know, temperature is a traditionally, conventional, is a statistical quantity. You know, if you imagine the temperature of this room, you imagine these air molecules moving quickly in a stochastic way. And if it is cold, they move slowly. If it is hot, they move, you know, all fast and quick. But this is a stochastic concept. So what is the real meaning of the temperature in the nanometer region? This remains to be established. Some authors claim that this very high temperature induces damage by itself, but this remains kind of doubt. The other effect, which seems to be a little bit stronger, is the story of the dissociative electron attachment and the water conduction band. So here is a strange effect, if you want, that means we saw many times, you know, the cross-section for ionization of the electron reach a maximum, you remember, about 100 electron volt, and then drops because, of course, the energy starts to be so low that there is no more ionization. But actually, this is true for the normal ionization. But if you have quantum effects like the dissociative electron attachment, so if the electron ends up in a band and creates a resonant effect, and this is, of course, a band in the water conduction band, then you can have further ionization even from electrons that are below the threshold for the normal ionization. This effect is a sort of, again, a sting in the tail of the electrons, if you want. So the possibility of the electrons, even when they are almost thermalized, almost without energy, to further induce damage in the DNA. And this is certainly something, you see, this is a famous experiment that was originally was published even on Science. It confirms the presence of these resonances. You see here, these are the double-stranded breaks so the lesion of the DNA on both strands, and this is instead the single-stranded breaks. And this is the loss of supercoil. So this means you break the molecule and it becomes linear. You see, for example, a resonance here, boom, a clear resonance when you are at 10 electron volt, which is below the energy for the ionization. How important is this effect? This is quite questionable, and it's quite questionable for various reasons. First, because these experiments are always done in dry DNA, because you need very, very low energy electrons, not in water molecules. And second, because this effect can be completely overwhelmed by the effect of that happens when the electrons have higher energy. So it's an interesting research topic in chemistry, but I think for the radiation biology, all these new effects, let's say, that come from radiation chemistry are not so interesting. The normal scheme that you have, you know, ionization, excitation, direct effect, indirect effect mediated by oxygen is everything you need to understand the next lecture that will be this is again the DNA strand breaks yield per incident electron, showing these resonances. The next lecture that will be about biochemistry. Actually, to be precise, as you know, the next lecture will not be on radiation biochemistry, but will be on pure biology. We will have a lecture only on biology, and that's because I want to make sure that when we start to go into the radiation biology, everybody understand the language that is, of course, different from the language that we use in physics. So that's the end of the lecture for today. Thank you very much, and I hope to see all of you next Wednesday. We will try anyway to discuss this lecture if there are questions, but also to go back to the exercises that we did last time. Thank you.